talking about matrices. So we are continuing matrices over R to be continued. So we said that determinant of AB is determinant of A times determinant of B, and we know this is for when the coefficients are coming from complex numbers C, then this is true. So we are going to see some discussion about this, why such a thing is expected over any commutative ring. So that I'm postponing because I want to do more of other theory, and then towards the end quickly I'll try to talk about this issue. Okay. So a lemma that so before I talk about this lemma, when am I going to say that a matrix is invertible? So A is invertible if there exists B such that AB is identity and BA is identity. So then question may be this identity, if A is an M by N matrix and B is an M by say N matrix, then the product is an M by M matrix. And other way product, if I change their position, then it is an N by N matrix. I expect both of them to be identity matrix. Then someone may wonder, so is it possible to have M different from N? So it's not possible. So maybe we'll summarize this here quickly. So first part, say, so here R is a commutative ring with unity. And this is a global assumption, which I may not repeat every time. A square matrix A is invertible if and only if A has got left inverse. If and only if F has got right inverse. If and only if determinant of A is a unit in R. So determinant should be invertible as an element of the ring. Okay, so we'll just see a quick proof for this. Suppose B is such that BA is identity. I'm not talking about what are their sizes. So for example, say A in part A, so I am assuming that A is a square matrix, so it is some M by M. Okay. So therefore, I'm also then B is also M by M square matrix. Or if this is BA equal to identity, then I can use that determinant formula which we have assumed, and I mean which we believe that it is true even over R. And later we are going to see that this belief is actually true. Okay, so applying this determinant, we know that determinant of B times determinant of A is 1, because determinant of the identity matrix is 1, and so then what we can do, then A inverse, I can say what is A inverse. Then A inverse is determinant of A, which is a unit, times what we define cofactor of A. That formula I can still use, right? The whatever formula. Okay, maybe I should say the adjoint, etc. So whatever formula we learned before, that can be used. Same adjoint formula works. Okay, so similarly for when you have a right inverse, the same thing will do, and therefore this part is fine. But for the part B, that if R is invertible, then A is a square matrix. So suppose again proof. Suppose A is m by n, B is n by m, such that when I multiply A to B, I have IM, identity matrix of size m. BA is IN, again identity matrix of size n. And without loss of generality, so I can assume that m is bigger than or equal to n. I mean, equality I want. Set k to be the difference, m minus n. Then what we can do, that I can adjoin a few 0 columns to A and a few 0 rows to B. How many? Namely k many columns. So I am supplying k0 columns, and here k0 rows. So still I will have IM, the identity matrix. And similarly, one can do that from here. Again, I can adjoin 0 rows here and columns 0 here, and I'll have identity matrix. Okay, so again I use determinant formula. So determinant of A with 0, determinant of B with 0 row is 1, which is false, a contradiction. Because unless k equal to 0, the left hand side you see this guy, determinant of A with 0, which is a square matrix and which has got a 0 column, and once you have a entire whole column is 0, then determinant has to be 0. So k must be 0, that is m equal to n. So A has to be a square matrix if A is invertible. Okay, so when we are talking about invertible matrices, we are talking about units. Okay, and besides M1R, when I have to think of the 1 by 1 matrix, M1 R. So here, when it is invertible, okay, so that means invertible elements here are nothing but GL1 of R, right? And what is GL1 of R? It is the group of units of R. So that means if I want to know group invertible matrices, I have to have knowledge about units of the ring. So just quickly see a few examples. Okay, so what is the group of units of integers? Maybe students can suggest what are 1 and -1 are the only possibility here. That's right. And if I have a field, F is a field, what are all units?
All non-zero.
All non-zero, correct. If F is a field. Or division ring also fine. If I have a division ring, then it is fine, but we are talking about commutative ring, so I did not write. Okay, what is the group of units of F square bracket X? Polynomials.
Power series with the polynomials with the constant term non-zero.
So that means what?
F minus 0.
F minus 0, correct. These are the same thing, what you are telling me, the same thing. That's good. And group of units of Zn, integers addition modulo n
Co-prime to
multiplication
n.
modulo n. I'm sorry.
So all n less than
Numbers
equal to
co-prime to
n,
n.
relatively prime to
Okay.
n. Yes,
Okay.
sir.
Okay. So since I am using n for defining the ring, I'll say that it is the classes in Zn such that what R is co-prime to n. That's right. So for example, if I want to know what are all units in Z6 or Z8, can you just dictate me? 1 and
5.
5 and
That's all.
that's all. For Z8,
1, 3,
1, 3,
3, 5,
5.
7.
5.
7. That's it.
Anything else? That's all? Okay.
No.
Okay, fine. So that's right. So this way we need to have see units. And there are more about units. If rings are changed, I mean, a group of units, it may be sometimes challenging to write down all units. For example, for ring of integers, for number fields, there are theorems related to units about structure of units. For example, what is the rank of structure of, So anyway, so to understand those also, we need to understand how to understand abelian groups. So that is the objective of this course also, to understand structure of abelian groups. Okay. Elementary matrices. So I am going again returning to matrices. I'm writing E to indicate identity matrix plus a scalar coming from R times Eij. Okay, where I is the identity matrix, so size n. Eij is the n by n matrix whose ijth entry is 1 and all other entries are 0, and A is an element in R. So there's such an element. This is invertible. This is an example of an invertible matrix, and this is an example of an elementary matrix also. Okay.
Sir, I think that pair you wrote I comma j, you mean I comma I think.
I comma I, no, I comma j. I'll come to back to this with some more examples. This is thus invertible. I'm just making, okay. So if you want to see an example of smaller disk size, say I can take this. Okay, so this is identity matrix, sorry, plus A, E, 1, 2. Is it fine?
Okay, sir. Okay, yes, sir.
Okay. So, all right. So this is one example. So this is an example of an elementary matrix. So another kind of elementary matrix is diagonal matrix, and one component, all other components are 1. Exactly one component is a unit in R. Okay, so I'll come back to this again, but let me recall what are elementary row operations. Row operations over R, because base ring is R. So all of you know elementary row operations. Interchange of rows, is it fine? Interchange,
Yes, sir.
of rows. So what does it correspond to? So for example, I have A, B, C, D. I want to interchange rows. I'll get C, D, A, B. Am I right? So we observe here that I apply the same operation on the identity matrix. Then it becomes 0, 1, 1, 0. Okay. Now, what I will do, I multiply 0, 1, 1, 0 to just the matrix I started with. Then what do I get? I get C, D, A, B. For a 2 by 2 matrix, we have just understood something, that interchange of rows of a 2 by 2 matrix is same thing as multiplying some matrix to that 2 by 2 matrix. And that sum matrix is what is obtained by interchanging the same pair of rows of the identity matrix. So what I will write in short, that an elementary row operation applying to a matrix A is same thing as apply the elementary row operation on the identity matrix and multiply it to A. You see this? This observation I am writing as an formula. This is an identity, and this is true for any elementary row operations actually. Okay, so this is one thing. Secondly, another thing is that applying this elementary row operation, namely interchange of two rows, is same thing as multiplying it by some matrix. And we have in fact given a description of that sum matrix. Okay, this is one type of interchange of rows. So next I'll go to another type. So maybe I say here 1, say that's next 2. What is the next? Multiplying a row by a unit. Unit in R. Okay. So A, B, C, D. If I apply such an operation, I'll get say lambda A, lambda B, C, D. So what am I doing? I am applying this operation. Operation is R1 replaced by lambda times R1. Okay, lambda belongs to the ring. I should write actually UR, right? UR, the group of units of R. Okay, so then this formula, this equality or identity, I want to write down. So this identity is now, I apply this operation on the identity. So this becomes lambda 0, 0, 1, right? And I apply this pre-multiply to AB, CD, and I get lambda A, lambda B. Sorry, CD. Okay, I'm sure all of you have seen this in linear algebra. And the third one, adding a multiple of a row to another row, right? So I just want to write down this last one. Say I want to apply the operation that R2, I want to replace by R2 plus, I'm multiplying the first row, some multiple, say mu multiple, mu times R1. Okay, so I'll get A, first row is unchanged, second row, C plus mu A, B plus mu, sorry, D plus mu B. And I'm saying that this is same thing as applying this operation on identity matrix, which 0 plus mu, then 1, A, B, C, D. So is it okay? Can I just leave it here?
Yes, sir.
Yeah, so since you know this, I'm just recalling what we know before. Okay, so similarly, we can apply elementary column operations. And for and if theta is a column operation or elementary column operation, then applying the operation on any matrix A is what is the formula analogous to this? Can you suggest me? Here row is a row operation. I am not writing elementary because even if it is a composition of row operations, still it is true. What am I supposed to write? What is the formula I am supposed to write here? In place of row A, I am writing theta A. Theta is a column operation. So I'll
theta I.
Right. I'll post multiply A by theta applied to I. Correct. Okay. So we'll switch, multiplying sometimes by theta I or applying the upper operation. All right. So and remark is that elementary row and column operations are reversible. You can get back the original matrix even if you apply finitely many elementary row operations or column operations or both successively, and from the resultant matrix you get a matrix from a given matrix, and from the resultant matrix you can get back the original matrix by applying a sequence of row and column operations. Okay, so what we are saying that from A I can apply sequence of elementary row operations and column operations and get A prime. Then applying a sequence of row operation and column operations, I can get back A. Row and column operations here also. Okay, so just recalling this fact. Okay, so now let us now go back to module. Suppose V1, V2, Vn are in V, where V is an R module. Okay, then W is defined to be this all linear combination A1 V1 like this, An Vn, which we in short maybe we can write like this: summation Ai Vi I equal to say 1 to n, where A1, A2, An are from R, is an R submodule of V called submodule generated by V1, V2, Vn. If V equal to W, then we say that V is generated by V1, V2, Vn. Okay. And V is finitely generated. Okay. Generated by these elements, and in this case we say that the module is finitely generated. If V has no finite subset, that generates V, then we say that V is infinitely generated. So this is about generation, and then linear independence. You can hear me?
Yes, sir.
Okay. So because I have to ask, because yesterday internet dropped and I did not realize initially. This set V1, V2, like this, Vn is, so this is a subset of V, and we are saying that S is linearly independent if any linear combination is 0 only when each coefficient is 0. Okay, so here AIs are coming from R. So equivalently, S is linearly dependent if there exists A1, A2, AN in R, at least one of them is non-zero, such that summation AI Vi is 0. For example, in Z3, 1 bar, 2 bar is linearly dependent, and since 1 bar plus 2 bar is 0 bar, right? How about only 1 bar? Is it linearly dependent? Anybody?
Independent.
No, this is also linearly dependent.
Yes, sir.
Why?
3 times I.
That's right. 3 times 1 bar. This is then 3 bar, which is 0 bar. Okay. So this is linearly dependent. See, where we are treating Z3 not as a vector space over Z3, as a Z module. Okay, so I'll just make it clear that the confusion, that if I want to think of the vector space, then she is right, that it is not. Maybe I make it clear here, the Z module, Z3, in the Z3 module, this singleton, which Z3 module? Namely Z3. Z3 is a Z3 module, right? This is linearly independent. Okay, so that way both of you are correct, but you have to see as what module. Okay, is it clear?
Yes, sir.
Here
Yes,
I am
sir.
supplying coefficients. In the first one, I am supplying coefficients from Z. In the second one, which I wrote in red and put in the bracket, coefficients are coming from Z3. So coefficients coming from Z3, I have only 0 bar, 1 bar, and 2 bar. So 1 bar and 2 bar only non-zero coefficients. So 1 bar into 1 bar is 1. 2 bar into 1 bar is 2 bar, non-zero. But in over Z, I can multiply by 3. And 3 multiplied to 1 bar is 3 bar. Okay, fine?
Yes, sir.
Okay. So again, in normally, I do not know, it depends upon where from you study linear algebra. So the following notation may not be standard there, but R13 follows this and it is very convenient. Namely, an ordered set subset B of an R module V is expressed as what? V1, V2, Vn. So sometimes people write V1 bar, V2 bar, Vn bar, but we are not writing any bar here. When we talked about vectors, we used to put bar. But when we understand that these VIs are coming from V, the module V, so it is okay, I think that, and or because it is ordered, so like n tuple, this is an n tuple, and every component is coming from V. Okay. And now we are going to talk about ordered basis. So, and an ordered subset V equal to V1, V2, Vn of V is called a basis if B is linearly independent and B generates V. So there is no change in the definition of basis. Only thing is that we have put a notation and directly gone for ordered basis, right? So this is actually an ordered basis. Okay.
Sir, this may
Yeah.
not be finite. The set B.
So it may not be.
Is there a condition that this is finite on finiteness or?
No, I am writing finite. Yes, you are right. You may not get a finite one.
Okay.
That is right. So we may not get a finite one. But since we are going to talk about matrices, etc., right now we are talking about finite only. Okay.
Okay.
Infinite situation is also there, but we are not discussing that right now.
So this is a finite ordered subset B in the first
Yeah,
line.
that's right. That's right. It's a finite ordered subset. And I am talking about basis that should be, then it is linearly independent and it generates the module. Yeah, for example, Rn, so B equal to E1, E2 like this, En. This notation EI are two standard, right? That ith component is 1, other components are 0, that is EI. So this is a basis of Rn. I'm dropping the word ordered basis, right? Ordered I'm not writing. Otherwise I am considering ordered. Okay. Okay. So this is a basis of Rn as an R module. So maybe I just say here what is EI. EI belongs to Rn. The ith component is 1 and other components are all 0. So this is the same notation used for our any field. Okay. So a definition, an R module which has a basis is called a free R module. The word free, now just we have introduced. If we can have a basis, then it is free. Okay. So vector spaces are free modules, right?
Yes,
Every
sir.
vector space has got a basis, so it is free. So now in the when we study modules, free modules are quite like vector spaces. There we have pieces. Our discussion about pieces, up to a great extent, we can do for free modules. Okay, we'll have more discussion now. Okay, so since you talked about infinite, just I write a remark that suppose S is a subset of V is an infinite subset, okay, then S generates V if, do you want to say anything? Every element of V is a finite linear combination. Maybe this finite I drop, I'll write later. Linear combination of finitely many elements from S with coefficients from R. Example, so Rx is an R module and S equal to 1 x squared, like this. All powers I collect here. This is an infinite collection, generates Rx. Okay, so in fact it is a basis and ordering is also there, but we are not going to use such a thing. So we are not going to discuss much about infinitely generated modules. Okay. If B is like ordered as V1, V2, Vn is a subset of V, then we write Bx to be what? This V1, V2, Vn, x1, x2, xn. Excuse me. Which is what? X1, V1, or maybe I multiply from right. V1, x1, like this, Vn, xn. Doesn't matter which order I multiply. Okay, so this is a notation, and this is notation is used in, I have not seen in many books. In eighteenth book, this is a notation used and very convenient. So we are going to see how it is convenient, how this is helpful. Okay, so is it okay that we are writing Bx? So,
Yes, sir.
and this defines, you see, this defines a map from R n, I have n vectors, to the module V. What is the map? If you give me any element here, x1, x2, xn, sometimes we can write like this also, x1, x2, xn transpose. Okay, and without transpose also this is okay if you want to adopt such a notation. So then I have an element in V. You see, this Bx is this. Is it fine?
Yes, sir.
Yeah. So x going to Bx. This is my x. This is my x going to Bx. So this is a map given a set. Sorry, this is given a subset, finite subset of V of cardinality n. I have a map from Rn to V. So I just write given a finite subset, may be ordered of cardinality, and we have a map from of V, maybe I write from Rn, where R is the ring, Rn is the free module, which is obtained by taking n-fold product, to V. Okay, so this is how you have to understand this. Then there are some interesting observations here. Observations. One, B, okay, if B generates V, see, B is a subset of V, right? So if B generates V, then what can I say about the map?
Map is onto.
Then this map, maybe I just write the map. Then Rn to V, what is the map? X map to Bx is surjective. You are right. 2, if B is linearly independent, then X map to Bx is, any comment?
Is 1, 1.
Injective. Is it okay for everyone? Why
Yes,
this
sir.
is injective? Subjectivity, I understand, it generates, so I get every element as a linear combination. Why it is injective?
The kernel is only 0.
Why?
Because
Why? Yeah.
the B is linearly independent.
So
We get linear combination.
right. So when it is
Plus
linearly
0.
independent, it is equivalently, if you write any element as a linear combination of elements coming from B, then there is at most one way of writing. So n comment is that an element of V can be written at most one way, as a linear combination elements from B. Am I right? So
Yes, sir.
please verify this one. This you have done for vector spaces. So I'll just write here, verify. Why there is only one way. It's a plain routine check. And combining these two, if B is a basis, then X mapped to Bx is an isomorphism of R modules. So we have talked about homomorphisms of R modules. If it is a bisective homomorphism, it's called an isomorphism. It is the same analogy. I mean, analogously, we define isomorphism here. Okay. So does an R module V has a basis if and only if, what can I say? That this basis has got size n, so Rn is isomorphic to V. Okay.
Yes,
And therefore, what we do, therefore, a module which has a basis, maybe I write R module, an R module which has basis is called a free R module. So what was the previous definition of R, free R module? What did you say there? If it is isomorphic to Rn, so what we have now learned that if it has got a basis, then it is isomorphic to Rn. So therefore, if we have a basis for V, then we are going to say that V is isomorphic. I mean, is a free module. Okay. So okay, so in linear algebra, perhaps a notation like this we have used. If V belonging to V is such that V is Bx. Okay, B is this same ordered basis. Okay, maybe I say that way. Next page. Suppose B equal to V1, like this, Vn is a basis. Then for V belonging to V, basis of V. Then for any vector, what I can say, if V is equal to B times some X, okay, then what can I say about X? X is the coordinate of V. This is the notation you used, right? Did you use this notation before? Yeah.
Yes, sir.
Yeah, this is the same thing. So I am not going to use this notation, but I am going to simply write this to mean this, the next one. Linear algebra. And this is a standard notation. Okay. Next, if B prime is again V1 prime, V2 prime, Vn prime is another basis of V, then suppose, or maybe define the matrix P, which consists of Pij, such that the new basis vectors Vj prime is a linear combination Pij of Vi, where I equal to 1 to n. Okay, so a priori you may say that how do you know that this basis has got equal number of elements, etc. Okay, so now this V prime I'm writing as a linear combination of Vi. So so in short, I can write B prime equal to B times P. Is it okay? Is this notation fine?
Yes, sir.
You
The
have
similar.
this B
Yeah.
dash and said it will have n number of elements.
Yes. So I have n columns.
Okay.
Okay.
Ha-
Or
no,
n elements. Okay, fine. N elements. And for example, V1 prime. How will I get it? I'll get it from the first column of P.
Sir, my question is ki B dash will it also, do we already know that it will have n number of elements?
Yeah, I'm writing if it is n, then this is fine.
Yes,
it?
yes. Okay. Yes, yes, yes.
So,
yes.
okay. So maybe I start write M. Okay. This is better then.
I
And
mean,
then
we-
J equal to 1 to M. Okay. Let us do this. So then I don't know whether P is a square matrix. Am I right? Right now we don't know.
Mhm.
Okay. So then I'll remove this one. So just think of this as what? V1, V2, Vn, and then column matrix to be P11, P21, Pn. How many?
There'll
N.
be M.
N1,
Yeah.
right? Then P2, P12, 1, 2, P22, then Pn2. Like this, P1m, P2m, like this, Pnm. Okay. So when I have x1, x2, xn, so I'll think of one column and multiply to this and get v1 prime. Next column will give me v2 prime and so on. So I'm writing them together in matrix form. So which I'm calling as BP in short. Okay. So I hope this is okay. Okay. So then we have to justify why P should be a square matrix. So let us write a proposition then. Okay. Proposition is that your query. The change of maybe part A. The change of basis. Sorry. Basis matrix in a free module is an invertible R matrix. So it should be in particular a square matrix. B, any two bases of the same free R module have the same cardinality. So then we'll be satisfied. So we have a little bit of time, so we'll just finish this here. If T prime is the change of basis matrix from B prime to B, then I can write B equal to B prime, P prime. And already we have, since already we have B prime equal to PP, we have B prime equal to BP. So I'll replace B by B prime, B prime, B prime, P prime, and I'll multiply P prime with P first. Is it okay? Okay, associativity of matrices will be helpful to justify this. Although B prime is not a matrix, it's a it has got vectors, a row of vectors. Okay, so this equality we have to believe or you verify it. Similarly, I'll have B equal to B equal to
P prime.
P prime. I'll take the first one, replace B prime equal to BP and B P prime, and put a parenthesis around this P and P prime. All right, so the change of basis matrix from B to B, similarly from B prime to B prime are what? From B to B I want to change. Matlab, we are not changing at all. Am I right?
Yes, sir.
So what should be the matrix? Change of basis matrix.
Identity.
Identity matrix.
That's right. Identity matrix. Is the identity matrix. So P prime P equal to identity matrix, and PP prime also identity matrix. So what am I supposed to write? Now can I expect that they have the same size? We know this, right? That they
Yes,
have to,
sir.
yeah, they are inverse of each other. Already inverse we have studied. Conclude that m equal to n, and what? Therefore B is proved, and change of matrix is a square matrix. Both are done together. Okay, A and B both are proved, right?
Yes, sir.
Yes.
Okay. Yeah. So a few minutes are still there. So maybe I just start the next point about matrices. First, a definition. The cardinality of a basis of a free R module V is called the rank of V. So if I can find a basis of a free module whose cardinality is say M, then I know that every basis will have cardinality M because of the lemma. Am I right? So therefore this definition,
Yes, sir.
rank is well defined. Cardinality of a basis of a free module is called the rank, and it is well defined because of the previous lemma. So in particular, V has to be finitely generated. Okay, there is no infinite basis. Every basis is of same size. Okay. And another remark is that if R is a field, then dimension of V is the rank. Am I right?
Yes,
This is
sir.
okay. So therefore, rank is a generalization of the concept of dimension. Okay. Fine. So next, I just want to start, but we'll then maybe have to stop in between. That is fine. Suppose V and W are free R modules. If F from V to W is a homomorphism of R modules, so I may not write every time of R modules, which is understood. Then define A belonging to M by N R. So I'm considering R modules and defining a matrix such that what I want, that maybe I say of rank M and N.
N and M. Sir,
N and
N. Yes, sir.
You can call
N-
N for, okay, N and fine, N and
N and M respectively.
right. So what is that matrix, how it should be? So I'm saying that if I have a basis, then I apply to this n tuple AX, that should be same as the map. Maybe I call this map as phi. Okay, phi of BX. So what am I doing? I have Rn, which is isomorphic to V, and I realize it by this basis. Then from Rm to W through C is a basis of W. Then from V to W, I have the map phi. I want to understand this Rn to Rm, which is multiplication by matrix A. Okay, so if I pick an element here, what am I doing? I'm multiplying by A. I want to I am defining A. What A should be? I'm claiming that it is such that Ax, when I apply C, I know what is C of a column of size M. I get an element in W. That should be equal to what? The same X, I apply B, I get an element in V, and then I apply phi on it. Okay. So this diagram is giving me this equality. Okay. So A is defined in this fashion. Is it fine? Definition of the matrix A, whose coefficients are coming from R. So
Yes,
then
sir.
lemma, which I'm not proving now because time is over, 1 minute already. So
Okay, sir.
if P and Q are change of, maybe I write in the next page. Change of basis matrices from B and C to B prime and C prime. You see, B is changed to B prime and C is changed to C prime,
Yes,
respectively.
sir.
Then the matrix A of phi changes to, that is also going to change A prime.
Yes, sir.
Then what is A prime? It is Q inverse A P. This is the statement. Okay, if A is a matrix of phi with respect to the basis B and C, then after changing B to B prime and C to C prime, and B to B prime, I know the change of basis matrix is B, and from C to C prime it is Q. Then the matrix A prime with respect to the basis B prime and C prime is given by Q inverse A. So quickly we'll see next time because time is over. And so I think I'll stop here. Is it okay?
Yes, sir.
Okay. So Professor Satyanarayana, you can